Okay, hello everybody. So this is the last lecture for the class. Before I begin, let me just make some quick announcements. Mostly administrative. So first one is that exercise 6 on the current homework is now a bonus problem. So you don't have to do it, but if you have done it or you want to do it still, you can, and it'll just be worth 3 bonus points instead of 3 points. And the reason is just because we're running a little bit behind of where I meant for us to be. So we haven't yet introduced the sort of character tables, and this question asked about a character table. So I thought maybe it'd be better to just make it a bonus problem. So we'll talk about character tables today, and then in our session on Tuesday as well. But anyway, I mean, it's at the end of the semester, so you guys are probably busy. So exercise 6 is bonus. Office hours this week. Well, the homework's due on Thursday, so I thought maybe I'd move the office hours to Tuesday. So office hours this week are Tuesday. (8:30 to 10:30), or 8:30 to 10, sorry. And these are the last office hours. Okay, because your exam is next week, your final exam. So let me just remind you the final exam is May 3rd. So that's next Tuesday, I believe, at 10:30 a.m. And so the details about this are on the website now. So if you just go to the website and scroll down to the exam section, there's some details. So, but in the short answer is it'll look pretty similar to the midterm. In particular, we'll be taking it on Zoom. Okay, but check those details. And then in the session in the in-class session on Tuesday, I'll start the session by just asking if anyone has any questions about that. So you'll have a chance to ask if there's anything you're concerned about. Okay, and then on the topic of homeworks and final exam, your problem rewrites for this second half of the class are due before the midterm starts. So on Gradescope, I think I set the deadline as 10:30 a.m. Okay, and I think there were fewer problems in this half. So I think there are just the week 9 homework, the week 10 homework, and the week 11 to 12 homework had a problem on them. But anyway, you can submit your rewrites if you'd like to. And then, right, Ellen, the last thing is please fill out, if you're registered for the class, please fill out the course feedback form. So you should have received that course feedback form via email. And I think there are only 5 students registered. So yeah, it will be very helpful for me if you can actually fill out that feedback form. I know it's easy to sort of let that thing slip, but especially since there are so few students actually registered, it'd be really helpful if those who are could fill out that form. Okay, so that's all the announcements. Let's get started with class. So let me recall the theorem we're trying to prove. So this is the main theorem of character theory. So it's if G is a finite group, and then sort of V1 through V K. I think I might have switched to M and K from last time, but let me use K here. So these are representatives for the isomorphism classes of irreps of G over the complex numbers. So irreps, again, is just short for irreducible representations. Okay, then the characters of these representations, the characters chi sub vi, determine, or sorry, are an orthonormal basis sorry, I can't spell today, orthonormal basis for the space of class functions, which we wrote CG. So these are complex value class functions. So these are functions on G, which are constant unconscious C classes. So F of conscious C classes. So F of GHG inverse is the same as F of H. And you could sort of think of that as just being a function on the set of conscious C classes, or you can think of it sort of being a G invariant element of the C brackets G, the regular representation. And there are different ways you can think of this, but just to avoid confusion, I want to sort of have sort of some specific notation for this. And so recall the inner product on here was if I had two functions f and h, or f and h, then their inner product was divided by the order of g, and then I just sum up over all the elements of g, the value of f on g times the value of h on g complex conjugate. Okay, so that was the main theorem we were in the middle of proving. And so what we did last time was we deduced some nice consequences. So we started before even proving the theorem. We explained that it had some nice numerical consequences for, like, for example, for classifying the irreducible representations of G. Like, it implies there are as many irreducible representations there are conscious C classes, because that's the dimension of this vector space. Implies that the sum of the dimensions squared of the irreducible representations is equal to the order of the G, the order of G, and so on. So a lot of what we're going to do today is just see how those consequences play out in some specific examples. We have to finish this proof because we didn't finish. Yeah, we only proved the orthonormality. So we only proved that they were orthonormal. We didn't prove that they were a basis. So right now what we need to do is prove that these representations span. So we need to prove the chi sub vi span CG. So orthonormal implies they're linearly independent. So if we know they span, then we know they're a basis. Okay, and so, well, we're going to use a standard trick for showing, like a standard trick for showing some set of vectors spans a vector space when you have an inner product, which is, it suffices to show that if f is an element, so f is a class function such that chi v sub I f is equal to 0. So it's such that this inner product is equal to 0 for sort of I equals 1. Okay, so k was the number of these irreducible representations. Then in fact, so anything that has inner product with these is equal to 0, then f is equal to 0. And indeed, this is, so what that means is you're showing that the orthogonal complement of So the subspace generated by these. So here, these brackets mean span, not inner product. So the orthogonal complement of this subspace generated by these guys is equal to 0. Okay, so that's equivalent to showing these vectors span CG. Okay, so let's expand out this formula. So given F, we can expand out what we get here from this formula. So do it. So chi vi F. Well, this is just the sum for all G and G. 1 over G times the sum over all G and G of chi vi of G times F of G bar. Okay. And we want to show this is 0. So let me just observe. Sorry, yeah, we're going to assume this is the thing we're going to assume is 0. For all I. Right. So if this is equal to 0, then well, we can basically ignore this factor. So then let me just get rid of this. So I'll multiply that. So then 0 is also equal to the sum over G and G of chi vig. I'm going to sort of just swap the order of these terms. And then I'm going to recall that in what is really chi sub vi of G, well, this is just rho, the trace of rho sub vi of G. So rho sub vi is an element of GLVI. So it's a linear transformation, and we're taking the trace of that. And now I'm going to do the following sort of funny thing. I'm just going to, instead of adding up multiples of the trace, I'm going to, instead of adding up multiples of the trace, I'm going to take the trace of the thing where I add up all the multiples. This is the trace. So I read here on the left, I'm pulling down 0. So I get sort of the 0 is equal to the trace of the sum of G and G of F of G bar. So this is a scalar times the matrix or linear transformation rho vi of G. So here, this is an element. Like this is a sum of linear transformations. So it's no longer, each of these rho vi's of G's is a GL of V. But when I sort of add up invertible things, like when I add up invertible matrices, they might not be invertible anymore. So this is just in end VI. So this is so the endomorphisms, that just means all the linear transformations, which is just and if you fix the basis, you can identify that with this n by n matrix ring, where n is the dimension of this of VI. Okay, so this element is this thing in here inside the parentheses is an element of sort of this matrix ring. So it makes sense to take the trace. Okay, so I get this endomorphism has trace 0 for each VI. And so the first thing I'm going to do is actually show that not only is the trace of this endomorphism 0, but in fact, this endomorphism is 0. So it's 0 itself. So let me change colors. So claim. So yeah, somehow, and this is the first step where we're going to bootstrap up to some more information. So we started just knowing this inner product was 0. We're going to bootstrap up to like finding out this whole endomorphism is actually 0. So it's not just a matrix whose trace is 0. It's really a matrix that is equal to 0. This is sort of the first place we get some more information here in this proof. Right, so how do we do that? Well, yeah, so the claim I want to prove is that the sum of G and G of F bar of G rho Vi of G is equal to 0 in this matrix ring. So that's the 0 linear transformation. Okay, and so, well, how do I show that? Well, it suffices to show that's equal to sort of some scalar times the identity element times identity linear transformation, because then sort of if the trace is equal to 0, well, the trace is just going to be sort of the dimension of Vi times lambda. Then that implies that lambda is equal to 0. So if I can show that this sort of this endomorphism is actually a scalar, then so knowing that the trace is 0 will tell me the whole endomorphism is 0. So when I say endomorphism here is interchangeable with linear transformation. It just means a linear transformation from Vi to itself. Okay, good. So that's why I want to show this thing is the multiple of a scalar matrix. So, well, I have basically one trick up my sleeve that can show me something is a multiple of a scalar matrix, and that's Schur's lemma. So I want to apply Schur's lemma. So Schur's lemma, which says this is true if this linear transformation is contained in the G invariant endomorphisms of Vi, because Vi is irreducible. So this is just so here's so Schur's lemma tells you exactly that. So for the irreducible representations, their G linear endomorphisms are their endomorphisms as representations of G are just the scalar matrices. Okay, so so we need to check this. Okay, so, well, and let's use this sort of second approach, the second definition. So it's sort of the G invariance where it's supposed to be the G invariance for the natural action of G on the space of NVI. So let's just take some element, let's call it H in G, and then we're going to check to see that this sum is sort of invariant on it. So then sort of the action of H, so let me write it this way. So the action of H on sort of this space of all endomorphisms, NVI, applied to sum of G containing G, so applied for this element we're looking at. Okay, well, it looks like sort of a mess, but I mean, if you just decode the definitions here, then and really we're just conjugating by rho sub vi of h. So we get, and you conjugate on the outside the whole thing, you pull it in by linearity through this multiplication by scalars. So this is f bar of g of rho sub vi of h rho sub vi of g, then rho sub vi of h inverse. So that's just coming from the definition of the action on endomorphisms. So the definition of this map rho sub nvi. But I mean, then we can simplify this still more. Writing this rho vi of hgh inverse. So that's just pulling in, sort of using that rho sub vi as a homomorphism. Okay, but now we're set because in f bar of g is equal to f bar of hg h inverse. Sorry, f of hg h inverse, because f is a class function. So class functions are constant, unconsciously classes, and so f of g is the same as f of hg h inverse. Okay, but now the sum we have is what we started with, just sort of, we've reordered. So we just sort of substitute hg h inverse for g. So let's just undo that substitution. Check. Okay, so that shows, so what this computation we just did shows is that when you apply some element, maybe we apply some element h of g to this endomorphism, it's preserved. I lost my bar somewhere, so let's just have a bar down here. So it's preserved. So this thing fixes. So yeah, this linear transformation of the endomorphisms sort of fixes this thing, fixes this specific endomorphism. So that means this thing is inside of the G invariant endomorphisms. And again, by Shor's lemma, that means it's just because VI is irreducible, that means it's sort of a constant multiple of the identity matrix, which is what we needed because that let us deduce that sort of the trace being 0 meant the thing was 0. Okay, so we've established this claim. Okay. So here VI, and VI was any VI was sort of any one of our representatives for the isomorphs class of irreducibles. So what this means is sort of this identity holds for any irreducible representation. So let me sort of say a consequence. I'll sort of switch colors back again. So the consequence of this sort of claim is, in fact, for any representation V, so for any representation V, this sum is equal to 0. So the sum over G contained in G, f bar of G times rho sub V of G is equal to 0 in sort of the ring of endomorphisms of V, the ring of linear transformations of V. And this is because sort of any representation V is sort of V1 to the M1 plus V2 to the M2, and we just decompose it into a sum of irreducibles, and then sort of rho sub V of G, and it's just, if I sort of write it in these coordinates, it's just going to be, so we'll get M1 copies of row v1 of G. So that's sort of acting on sort of the first part. So this is M1 row v2 of G for sort of so on. So I get M sort of M2 row v2 of G's and so on. So I sort of, the point is, elements are preserved sort of each sum end in this decomposition. Okay, and so then, and when you write out this identity, like when you write out this thing, and you now you write out this linear combination of row v of G, sort of all over all G's. Well, then you just expand out in each sort of each of these terms, and sort of in each of these terms you get 0. Okay, so that tells you that this is the 0 endomorphism sort of on any representation. So now we conclude by taking V to be the regular representation. So then if I look at sort of this thing, F bar of G, row V of G, and I hit just the identity element with it. So the identity element is something in its regular representation. So it's 1 times the regular element. Well, I'm just getting the sum over all G contained in G of F bar of G times G. And so that's equal to 0 by this consequence. So, but that implies, I mean, these different symbols G in the regular representation, they are a basis for the regular representation. That implies F bar of G is equal to 0 for all G and G. Okay, and that's what we wanted to do, right? So let me sort of trace back. Let me go back to the start and sort of trace what we did in this argument. So, right, we're trying to prove this theorem that the sort of characters of the irreducible representations were an orthonormal basis. Last time we proved the characters were orthonormal. This time we're just left to show they were a basis. Okay, and so we did sort of the standard thing when you have an inner product, which is if you want to show some subset spans everything, then it's enough to show that if you have some other function which is orthogonal to all the things you're starting with, then that function has to be 0. So it's sort of enough to show the orthogonal complement is equal to 0. Okay, so we get this, and we take some f such that 0. We take some f that's in the orthogonal complement of all these guys, and what we get. So from the identity that 0, this inner product is 0, is that the trace of sort of this matrix living in sort of endomorphisms, this irreducible representation is 0. But in fact, so we can bootstrap that up to show the whole endomorphism is 0. So and this is for each VI, because in fact, sort of this endomorphism isn't just any endomorphism; it's a G invariant endomorphism. So Schur's lemma tells us. So here was the calculation that was G invariant. So it used the fact that f was a class function. But then Schur's lemma tells you that this thing is some just scalar multiple of identity. And so if its trace is 0, then the whole thing is 0. Okay, so we get that sort of this is 0 for each irreducible representation. But then using sort of complete reducibility, that implies that sort of this same kind of sum is equal to 0 in the endomorphism ring of any representation. Okay, good. So okay, so that's quite nice. And then to finish, we just apply that to the regular representation. So you take this this endomorphism, you apply it to just the identity element, so 1 times identity element, the regular representation. Well, you just get sort of the sum over G of all the elements of G of F bar of G times G. And so if that's equal to 0, well, since these sort of symbols G are a basis for this vector space, you get the f bar of g is equal to 0. So all the for all g, all the coefficients. Okay, so finish the proof that these things span, and thus finish the proof of this very nice theorem. Okay, so let's now take some time to illustrate how you can use this. Okay, so let's talk about irreps of S3. This is a baby case, and we'll do S4 next. Okay, so well, okay, we know what these are. There's a trivial representation, the one-dimensional trivial representation. Yeah, let me sort of set this up actually like this. So there's a trivial representation. There's the sign representation. And there's a standard representation. So standard is just sort of x, y, z such that x plus y plus z is equal to 0 in C3, where the action is by permuting the coordinates. Which is equal to sort of the orthogonal complement of the trivial representation living inside of here, which is just the span, sort of the sub-representation where everything is equal, where x, y, and z are equal. Okay, so that's the trivial representation, sign representation, and standard representation. And well, there are also only 3 conjugacy classes in S3. So there's the trivial conjugacy class. There's a conjugacy class of transposition, and there's a conjugacy class of a 3-cycle. Here, this conjugacy class has 1 element. So there's 1 trivial element. There are 2 3-cycles, and then there are 6 choose 2, or 3 choose 2, so 3 2-cycles. Okay. Okay, so there's 3 conjugacy classes, and we already know about these 3 irreducible representations. So that's actually all of the irreducible representations. And so it's sort of convenient to package the information about these representations, their characters, inside of a table. So this is called a character table. And so each row is just going to be the value of that character. And so, well, since the value of the character is a class function, since the character is a class function, we only need to know the value on sort of a single element of each conjugacy class. So that's why we sort of write down just 1 column for each conjugacy class. Okay, good. So let's do that. Well, the character of the trivial representation is it's just 1, so 1 across the board. Because every element just goes to sort of the 1-by-1 matrix, the 1-by-1 identity matrix. Okay, and the character of sign representation, well, the sign representation is, again, it's 1-dimensional. So the character of a 1-dimensional representation is sort of just the same as the value of that representation. Like a 1-dimensional representation is the same as a map to C star. Okay, so the sign representation, well, 1 is even, so it goes to identity matrix to get 1. The transposition is odd, so it goes to -1. And then a 3-cycle is even again, so you get 1. And then, okay, now we're left with the standard representation. So this first column is easy because, so just like the sort of first row was easy because there's always 1 straight across. The first column is also always easy because somehow you're just getting the dimension of each representation. So good. So you're just getting the dimension of each representation. So the dimension of this one is 2. So it's a complement. So it's a cut up by one equation in 3-dimensional space. So this is 2-dimensional. Okay, and then the complement of okay, but then we have sort of these 2 columns we're left to compute. So let's just do them. So to compute these remaining columns, we can use that. Well, because C3 is equal to so this is a computation we did in class session, like the problem session, but let me just recall. C3 is sort of triv plus standard. So that means that the character of C3 is the character of triv plus the character of standard. So that means the character of the trivial representation, or the character of the standard representation, is the character of this permutation representation minus 1, minus the character of the trivial representation. So this means that if you take the character of the standard representation on some element G, well, from this first part, you just get the number of fixed points of G. And then subtracting out the trivial representation, you get -1. Okay, so good, that checks out for the identity element. The identity element fixes 1, 2, and 3, so there's 3 fixed points, but you subtract 1, so you get 2. Here, this thing, a transposition fixes has 1 fixed point, so you get 0. Whoops. Because 1 fixed point minus 1, you get 0. And then a 3 cycle doesn't fix anything. So you get 0 minus 1, you get -1. Okay, and so in this table completely encodes the representation theory of the symmetric group. And we can check sort of various things. And you can check sort of various things that we know are true from this table. So for example, we know that the characters are sort of orthonormal for this inner product. So that means sort of, well, if you add up this, and you add up the absolute value squared in each row, you should get the order of G, except you have to multiply sort of each one by the number of elements in the conjugacy class. Because here, sort of we're only like here we're only sort of writing down 1 column for each conjugacy class. So for example, like the fact that chi vi is equal to 1. Well, this is in this example, we just see when the first row, this is 1 squared plus 3 times 1 plus 2 times 1 equals 6, which is the order of S3. So good. In the second row, so this is for the sign representation, this comes from 1 times 1, so 1 plus 3 times 1 again plus 2 times 1 again equals 6. So here you take the square of the absolute value. So this 1 is equal to sort of -1 times -1 bar, which is equal to just -1. That's the value of -1 squared. And like it's possible sort of to get complex numbers here. So so the formula to remember is square of absolute value. And then sort of the standard representation, we're getting 1 times 4. So this is equal to sort of 2 times 2 bar. So coming from this first entry, plus 3, so 3 because there's 3 in this conjugate class, times 0 squared. So just 0 plus 2 things in this conjugacy class, times 1, sorry, times minus 1 squared. So minus 1 times minus 1 bar is equal to 6. Okay, so this, in terms of this character table, like this identity, you know that sort of the inner product of any irreducible character for itself is equal to 1, just translates is you use a sum sort of the squares of the absolute values sort of times the number of elements in each conjugacy class, like along each row, you get the number of elements in the group. And so the reason you get the number of elements in the group instead of 1 is because in the definition of the inner product, you sort of divide by that number of elements of the group. So similarly, we have the identity like chi of vi, chi of vj is equal to 0, sort of I is not equal to j. So to these two distinct irreducibles, you get 0. Well, if you check in this example, and that's just, I mean, that's always just true. So this is always equivalent to saying the rows of the character table are orthogonal. So for the standard Hermitian inner product. So and here, 1 times 1, sorry, for the standard Hermitian inner product, so times weighted by the conjugate classes again. So 1 times 1 times 1 plus sort of 3 times 1 times minus 1. So that's 1 minus 3 plus 2 times 1 times 1. It's 1 minus 3 plus 2. That's equal to 0. So it's sort of these rows, like orthogonality of sort of distinct irreducible representations sort of gives you sort of some orthogonality of these rows. Okay, where you sort of have to remember to multiply sort of the entry you get from each column. There's sort of the sum you get from each column by the sort of the number of elements in the conjugacy class. So that's why we sort of write the number of elements in the conjugacy class up here. Okay. There's other things that are going on here too, though, which is sort of nice. So, for example, if you look at this column, this first column, so we're getting sort of that the 1 squared plus 1 squared plus 2 squared is equal to 6, which is the size of S3. So if I just sum the absolute value squared in the column instead of the row in this first column, I'm getting, well, okay, well, I'll tell you in a minute why, like a different reason we get, besides what we've already talked about, why you get the order of the group. But it turns out sort of you're going to get the order of the group always. And good, but that's an identity we've already seen. And then the reason sort of we already know that is because like the trace of the identity element is just dimension of the representation. We already explained why the sum of sort of the dimensions squared is equal to the order of G. So we explain that using the regular representation. And in fact, something similar holds for each of these columns. So let me sort of wait. So now I'm gonna if I sort of take 1 plus, oops. Okay, let me write this somewhere else actually. So if I take, I know what I'll do. Make myself a copy of this character table. I'll pull it down here and then I can sort of keep on going. Sorry, like only as the semester ends am I sort of learning how to actually use functionality usefully. So okay, so now I can look at this sort of second row. And so I have 1 squared plus minus 1 squared plus 0 squared. This is equal to 2. Okay, so let me hold off for a second, do the next one before I explain the significance, like explain what 2 is here. So I get here 1 squared plus 1 squared plus minus 1 squared. This is equal to 3. And it turns out sort of the commonality is here, and this is 2 is 6 divided by 3, and this 3 is 6 divided by 2. So this is, and both of these are the number, so the size of your group divided by the size of the conjugacy class. So if I sort of sum up the squares of the absolute values of entry in a column, I get the order of the group divided by the number of divided by the size of the conjugacy class. And sort of similarly, yeah, and so that checks out in both of these. So the 3 was the number of elements in this conjugacy class, and the 2 was the number of elements in this conjugacy class. Okay, great. And well, here, the reason we just got the order of the group when we did it in the first column is because the identity element sort of always has just sort of a single element in this conjugacy class. Okay, so let me sort of state this as a result. Oh, sorry, I forgot the other thing. I mean, if you look, the columns are just straight up orthogonal. Like, so if I just take the inner, there's no weighting here, so I just take the inner product, like 1 times 1 plus 1 times minus 1 plus 2 times 0, I get 0. And so I do 1 times 1, minus 1 times 1, 0 times minus 1, 0. 1 times 1, 1 times 1, 2 times minus 1. Add those up, I get 0 again. So the columns are orthogonal, so distinct columns are orthogonal to each other, just for this sort of standard Hermitian inner product without. Okay, so in the rows, you always have to weight by this number of elements in the conjugate class. And the columns, you don't have to weight by that when you're sort of looking at 2 separate columns, though it does sort of come up when you do one column with itself. So this is called second orthogonality. And so this just says the columns are distinct columns in the characters table. So for any group, distinct columns in the character table are orthogonal. So any sort of group, it's any finite group into the character table of the complex numbers. So distinct columns are orthogonal. And any, so the column CI sort of corresponding. So the column corresponds, so the column C corresponding to a conjugacy class. So called script C, the conjugacy class, satisfies C dot C bar. So that's just the standard Hermitian inner product itself is equal to the order of G divided by the number of elements in the conjugacy class. Okay. So, and this is quite nice that, I mean, so we don't just have these orthogonality relations we already talked about that sort of relate sort of one representation to another, the trace of character of one representation to the character of another representation. Like we also sort of have some relations that express sort of the values for all characters of representation sort of on different conjugacy classes. Sort of say those satisfy some nice relation. So this is a very powerful theorem this is a very powerful observation for computational purposes, for like letting you try to compute irreducible representations of groups. So we'll see that in an example in a moment. Right, let me just make one remark on the proof. I mean, the idea is that the character table is just a change of basis matrix. So it's the change of basis matrix from the basis, so the indicator functions. So the indicator functions for the conjugate classes. To the characters. The characters of the irreps. I might have this in the wrong order. Or maybe it's, and probably what's true is, okay, so it's looks like it's the transpose of the yeah. So it's the transpose of a change of basis matrix from these indicator functions of the variables, the indicator functions of the conjugacy classes to the characters of the irreducible representations. So it's the change of basis matrix. But so this is an orthonormal basis. And this is almost an orthonormal basis. So it's orthogonal up to so it's orthogonal, but the inner product of sort of one of these guys of itself is not it's not one. It's actually, so it's the number, it's the inverse of this number here. It's sort of the number of elements in the conjugacy class divided by G. So they're orthogonal, but you have this, the inner product of the indicator function with itself. You just sort of compute that out, you get the number of elements in the conjugacy class divided by G. Okay, so but that means, so this matrix is sort of basically unitary. So i.e. it satisfies A times A transpose complex conjugate is equal to, so well, it's not quite unitary. So what it satisfies is sort of, well, it's some diagonal matrix. Okay. Sorry, I'm just, yeah. I guess I should get, yes, I'm confused now whether I should get to G over C or C over G. Probably I should get this one, but let me not write down. But one of these things is going to be sort of the diagonal entries. Okay, so sorry for being confused with that. But then that means that sort of also this guy is sort of diagonal. So if I sort of just take the so sort of, and the idea is sort of unitary means so if I write A star is equal to AT bar, then sort of unitary is A star is equal to A inverse. So that means like A star A is equal to ID, and then also A star is equal to ID. Okay, so same idea here, just sort of there's this normalization issue where one of these matrices, one of your bases is not quite unitary, sort of orthogonal, but sort of the inner product's not equal to 1. but you still get the same kind of identity. Okay, and if you expand this out, like one of these is first orthogonality, like one of these identities is first orthogonality, and the other is, so I'm going to say this and this. So the matrix is unitary, so this holds, but also this holds. So one is first. Yeah, let me not try and sort out which. One is first orthogonality, the other is second, or the other identity is second orthogonality. So and there are different ways you can think about this, but that's at least one of them. Okay, so let's so yeah, that's a proof of second orthogonality, but the main thing to remember is just actually the statement, and the statement is sort of super useful in practice. Let's do a final illustration of how it's useful, and that will sort of wrap things up. And I guess I'll make a few remarks after this example. So we're gonna do the character table of S4. Okay, so let's, maybe we'll color code it a similar way. Well, okay. My color coding wasn't amazing either, so let's think ahead of time how we want to color code it. Let's do the conjugacy classes first. So we have the identity element. We have 2 cycles. We have 3 cycles. 4 cycles. And there's only one possibility for sort of having 2 different cycle types, non-trivial cycle types, and that's you could have a pair of 2 cycles. So we have 1, 2, 3, 4, 5 conjugacy classes. And let's write in the number of elements below those. So that was 1. Then there are 4 choose 2, so 6 transpositions. 4 choose 3 times 2, so 8 3 cycles. Then 6 4 cycles. So just 3 factorial. And then 4 choose 2 divided by 2 pairs of 2 cycles. That's 3. That should add up to 24, and it does. Okay, good. So those are the conjugacy classes, and then we'll write down the representations. So and we'll just start with what we know. So we have triv, and then we have the sign representation, and then we have the standard representation. So we talked about this in our session. Again, the problem is so the standard representation is always irreducible. Okay, so that's what we know about so far. So let's go ahead and fill in what that gives us. So yeah, let me draw my lines. So we have fun color for filling in. So okay, so triv, this is one-dimensional, and standard is 3-dimensional here. Okay, and trace identity element is always just the dimension of the representation. Then let's go across. Trivial representation is always easy to fill in because its trace is 1 on every element. Good, and then the sign representation, we just need to know whether permutation is even or odd. So odd gives -1, even gives 1, odd gives -1, and then even gives 1. Check. And so if you're ever worried, and when I say when you're filling these in, it's like you're ever worried you've made a mistake, you can like check the orthogonality relations. So if you want to like a sanity check, you can just check the sign, so that this row, so inner product of this row is 0. So we take this weighted dot product, we rate by the number of elements, and we get sort of -12 from these 2 things, and then +12 from these 3. So that's equal to 0. Good. checks out. Okay, and then the standard representation. So the same formula for the standard representation holds. It's the number of fixed points minus 1. So here, 1, 2, this has 2 fixed points, 3 and 4. So when we subtract 1, we get 1. This guy has 1 fixed point. So subtract 1, we get 0. This one has no fixed points. So subtract 1, we get minus 1. And similarly over here, so subtract 1, we get minus 1. And maybe quick sanity check, and we can check some orthogonality to make sure we did this computation right. So like 3, so let me sort of check with the trivial representation. So 3 plus 9 plus 0 minus 6. So minus 3, that's 0, good. So we have 3 plus 6, minus 6, minus 3. Then let's check with the sign representation too. So 3 minus 6 plus 6 minus 3. Okay, check. So this thing is orthogonal to the first two. So that gives some confidence to our initial to the computation I said out loud. Okay, and so this is where we're at. And well, but we also, and we know how many sort of rows we're supposed to get. We know we're missing 2 irreducible representations. Well, and we also know like, yeah, so, okay. One of them is easy to find, it turns out. So it turns out sort of if you take any irreducible representation and you multiply it by, you take the tensor product of the character, you always get an irreducible representation. It might be the same irreducible representation. Like you might not change the representation by tensoring it with a character, but if you change it, then it's new. In this case, you're really going to change it. So and let's compute the character, and then I will explain sort of why it's still irreducible. So the character, well, tensor product just multiplies the characters, so we get 3. Of course, and tensor product between a 3-dimensional thing and a 1-dimensional thing is still 3-dimensional, so that's good here. But in general, so yeah, so we 3, then we get, just multiply these, we get minus 1, 0, 1, and then minus 1. Okay, good. And so this is different than the standard representation because, for example, these entries are different. But in the only change was like some entries got multiplied by minus 1. Like these 2 entries got multiplied by minus 1. So that means, but like if you compute the inner product of sort of this character with itself, you're going to get the same answer you got for this for the standard representation, because you're just taking the sort of the sum of like the sum of the squares of the character, or like the sum of that absolute value squared of sort of the values of the character. And so when you multiply that by like when you multiply the value of the character by minus 1, like you're not changing its absolute value. You're not changing the absolute value squared. And so similarly, the same will hold always for any character. So in general, characters are valued in roots of unity. And this is essentially something we saw already. But characters are always, they take values in roots of unity. And so then when you sort of tensor with a character, you're just sort of multiplying all of your entries by some roots of unity. So you're not changing sort of whether something's irreducible, because you're not changing its inner product with itself. So remember, yeah, this is something we did in the problem session, but just recall the fact I'm using here is the character, a representation is irreducible if only if its character of itself, the inner product of its character of itself is 1. Okay, but good. So that got us a new irreducible representation is the point. So we added 1 row here, and now we know we have 1 left. And like the amazing thing is, even though I'm not going to construct this representation, I know it exists, and I know it turns out everything about it using the orthogonality relation. So, for example, I know the sums of the squares. I know the sums of the squares have to be equal to I know the sums of the squares of the dimensions have to be equal to the order of the group. So let me recall the order of S4 is 4 factorial, so that's 24. And so here I'm getting 1 squared plus 1 squared plus 9 plus 3 squared plus 3 squared. So that's 1 plus 1 plus 9 plus 9. That's 20. So I'm left with sort of 4 I need to get. And so that means sort of this last thing has to be 2, because remember I'm adding the square. So I'm getting some 2-dimensional representation here. So 1 plus 1 plus 9 plus 9 plus 4 is 24. Okay, so whatever this mystery object is, it's 2-dimensional representation. Okay, and then I could do the, so here I could sort of try doing the same thing in each column, but I would sort of, I'd only sort of get sort of what this, I get sort of the absolute value squared. If I sort of try to do the things in the other column, and like, so in this first column, I knew the entry had to be positive. So I knew I couldn't get a -2 here because this is going to be the dimension, it's the trace of the identity element. But these other columns, you don't know you're going to get a positive number necessarily, or even like a real number. But that's okay. Like, there's actually an easier way to do it, because I know that like the dot product of this column with this column is going to be equal to 0. So I get 1 plus -1, so 0, plus 3 plus -3 is 0. So when I sort of take this dot product, already I'm at 0. So that means that I better have a 0 here as well. So this is 0. Okay, here I'm getting sort of 1 plus 1 times 1 plus 1 times 1, so that's 2, and zeros. So I sort of have 2 up to here, so I have to kill that off to be orthogonal. So this, now I have to get -1 down here for the dot product for this column with this column to be equal to 0. Okay, and so I keep on going. So 1 -1, so these are 0, -1, 1, this is 0, so this one gives me 0 again. And then here I'm getting 1 plus 1, so 2, -3, -3, so I'm at -4 now, so I better get 2 here. Good, and then sort of just to sanity check, I could sort of check to make sure that this thing is, or like this row is now orthogonal to these other rows. So for example, I could check like 2 times 0, 2 times 1 is 2 plus 0 plus -1, so 2 minus 8 plus 2 times 1 times 3, so 6, 2 minus 8 plus 6, that's, yep, that's 0. It's okay, so this row is orthogonal to this row. Again, when you're doing the rows, you weight by the number of elements in the constancy class. Okay, good. So this, and with high confidence, well, with mathematical 100% confidence and sort of high confidence that I didn't make a computational mistake, this is the character table of S4. And what was amazing is that we sort of computed this last row without constructing this 2-dimensional representation. So that's sort of amazing that we were able to just use the numerics of the situation to deduce so the trace of every matrix in that representation, even though we didn't give an explicit construction of that representation. Like, we know there exists some irreducible representation where the traces of all the matrices are given by sort of these numbers. Yeah, so this is sort of fun, and you can really you can compute things. You can compute sort of all of these invariants in representation theory without actually like knowing how to construct the representations themselves. And like, I mean, this is a very powerful technique, both in somehow even internally within group theory. Like, sort of in the classification of simple groups, I mean, one thing that happened is sort of people sort of wrote down the character tables of groups, like sort of, and you found sort of simple groups, and then you sort of deduce the character table of that simple group, like had to sort of be this thing. I mean, sometimes before the group was even sort of shown to exist. So like, yeah, and this is a very, very powerful and interesting technique. Okay, so that's the last topic I wanted to cover, last example I wanted to cover. I want to just finish with 2 remarks. So I'm basically just done examples and computations in the lectures, but and there's some nice basic applications of sort of this stuff of this representation theory to Galois theory that are in the homework. So for example, the normal basis theorem and as a result of it, Kummer theory basically follow, and they're completely elementary from a representation theoretic perspective. So that gives you sort of just a window into like some possible applications, but in representation theories, and it's one of those things that's applicable all over the place, just because there are, no matter what kind of math you're doing, you're going to run into objects whose sort of symmetries, and you're going to run into linear objects whose symmetries are groups. And so then representation theory sort of governs how you can structure that information. So keep your eyes open and you'll run into representation theory outside of this class as well. Okay, that's one thing I wanted to mention. And then the other thing I wanted to mention is that so there's this other approach based on group algebras. So if you look at this thing that I was calling the regular representation before, like CG, like, and well, it's a vector space and it's a representation, but actually like this has a natural algebra structure. This is a natural C algebra. It's not necessarily, if G is not commutative, this is not commutative, but it's the multiplication is just the obvious multiplication, like so G times H is equal to G times H. So you sort of let your basis elements multiply together in the obvious way. And so this gives you a sort of a finite dimensional algebra of the complex numbers. And it's sort of semi-simple. So that's another formulation of sort of complete reducibility. Okay, and sort of C could be replaced with sort of a different field K here. And well, you could anyway, you can develop sort of the whole theory from this perspective too. And one nice way to do one nice reason to do this is because then sort of somehow a lot of the statements, and a lot you don't see character theory, for example, if you do that. But you see that, I mean, you see these things I pointed out, that the structure is sort of much simpler than you a priori expect. And the reason is, I mean, there's a theorem that says, like, well, over the complex numbers, like any finite dimensional semi-simple group algebra is just a product of matrix rings, as a product of matrix algebras. So there are sort of other ways that sort of you see immediately that there's going to be a nice structure when you sort of organize things through this approach. And of course the two approaches are related. So they're related. They're related sort of through this kind of construction we did at the start of class today, where we looked at, we sort of looked at this element sort of that was acting sort of by an endomorphism, like it was acting on sort of every irreducible representation, but really sort of was acting on every representation. So somehow there's a more categorical way to sort of phrase sort of passing from like representations to group ring, and the idea is when you have a representation, like you don't just sort of get the action of G, like you get sort of the action of all these other endomorphisms too. And so, to state it in sort of sophisticated language, we'd say is sort of you have the category of representations and you have like the forgetful functor. And then sort of this forgetful, so the forgetful functor, the vector spaces, this forgetful functor sort of has endomorphisms as a functor, and sort of the ring of endomorphisms, the forgetful functor, is just the group algebra. Well, and then this construction we did above is sort of, it's just computing that the center of the category is sort of identified with class functions. So there's sort of a nice categorical way that plays some importance in more sophisticated realms of representation theory to think about relation between these two. But anyway, well, they're both sort of useful perspectives, and what's really useful is actually this relation between the two. But this is sort of a topic for another time in another course. Yeah. Okay. So anyway, thank you everybody for attending the course, and I'll see you on Tuesday in the problem session. And again, if you're registered for the course, please fill out the course feedback, which you should have a link to in your email in some way or another. Okay, thank you, and I will stop the recording.